Welcome! Today, we're diving into the basics of current electricity and magnetism from Class 8 Science, Maharashtra Board. We'll answer questions like, how do objects get charged? What's the difference between static and moving charges? And how does electricity flow in a circuit? Let's start by understanding charges in an atom. An atom contains positively charged protons and negatively charged electrons. Even though these particles are charged, an atom doesn't usually show any charge because the protons and electrons balance each other out. This means the objects around us are filled with plenty of electric charges, but they don't appear charged overall. So, what happens if a glass rod is rubbed on a silk cloth? Rubbing transfers electrons from one object to another, creating an imbalance of charges. This is how objects can become charged. Static versus moving charges. The electrons in an atom can sometimes be set in motion, creating a flow of charge. When charges are static, they stay in one place. But when charges move from one place to another, we have what we call current electricity. These moving charges are electrons, the negatively charged particles that can be transferred between objects. Current electricity and potential difference. You may have seen lightning, which is a powerful example of electricity moving from clouds to the ground. This is a large current. In our everyday lives, though, we encounter smaller currents in wires, electric bulbs, and batteries. In an electric cell, current flows because of the movement of charged particles between the terminals. Think of electrostatic potential as similar to water flowing downhill. Here, electricity flows from higher to lower potential. The difference in electric levels between 2 points is called the potential difference. When we connect a dry cell in a circuit, this potential difference pushes the electrons to move, lighting up the bulb. No cell, no potential difference. No potential difference, no current flow. The SI unit for potential difference is the volt, while the unit for electric current is the ampere, or A. Types of electric cells. To keep electricity flowing in a circuit, we need a constant source of power like an electric cell. Dry cells are used in torches and clocks and have a zinc layer as the negative terminal, with a graphite rod as the positive terminal. Lead-acid cells are another type, often found in vehicles, and can be recharged after discharge. Nickel-cadmium cells, or Ni-CD cells, are also used today in gadgets, providing a 1.2 volt potential and can be recharged. Building an electric circuit. An electric circuit is simply a path through which current flows. When we connect a dry cell, bulb, and key in a circuit, closing the key allows the current to flow, lighting up the bulb. But if we remove the cell or open the key, the current stops and the bulb turns off. Circuits allow us to control the flow of electricity. Connecting more than one cell in series, like in a radio, creates a battery, allowing for a higher potential difference and thus a stronger current. Magnetic effects of electric current. Electricity and magnetism are closely related. If you pass an electric current through a wire, it creates a magnetic field around it. Ørsted first observed this magnetic effect, which we can demonstrate with simple activities. By winding a wire around an iron nail and passing current through it, the nail becomes an electromagnet and can attract small iron objects like pins. The electric bell. An everyday example of an electromagnet is the electric doorbell. Inside the bell, a coil of wire wound around an iron piece creates a magnet when current flows through it. This magnet pulls an iron strip, causing a striker to hit a gong. As the iron strip moves back, the circuit closes again and the bell rings repeatedly.